substitution and elimination. I did so much talking for the last few days that my voice is sort of shot, but I'm trying. So. We talked a little bit about this back in chapter 6. We'll review what we said there, and then we'll move on to elimination reactions, and then talk a little bit about the obscure art of choosing whether or not you want elimination or substitution to happen. And it is a bit of an art, to be honest. We've talked about polar covalent bonds. We know that in something like chloromethane, because the chlorine is more electronegative, it will polarize the bond between the carbon and the chlorine, so that in the electrostatic potential map, we have high electron density at this end and low electron density down here around the carbon. Now what this does is it makes the carbon susceptible to nucleophilic reaction. So let's look at that. Here's our chloromethane, and this is chloride. Now, chloromethane, as we just said, has a positive end down here by the carbon, and the chlorine of chloride, of course, has a nice anionic electron cloud around it. Because this is positive, it is seeking electrons. And remember, we call that electrophile. It's also referred to perhaps more properly as a Lewis acid, but electrophile will do. So this carbon wants electrons. Up here we have chloride anion. It has extra electrons, nice rich source of electrons. What's going to happen in a simple substitution is that the chloride is simply going to attack this positive carbon. We're going to lose our leaving group here and form a new product. The reaction itself looks something like this. As our chloride, our chloromethane, what we're going to do is attack positive carbon. As we do that, we have to break the bond to our leaving group here. That will be a chloride also. We now have another molecule of chloromethane and, of course, chloride anion. We said that this type of substitution reaction was going to be called an Sn2 reaction. That goes for substitution, nucleophilic, bimolecular. Now, substitution makes sense. Nucleophilic, because we have a nucleophile and an electrophile. Bimolecular refers to the kinetics of the reaction. And we'll talk about that in just a moment. A very simple example of a substitution reaction. If you take something like 2-bromoethane, that's this guy, and we have methoxide anion. This is our nucleophile. Because it has lots of extra electrons, is looking for something positive. This carbon will be our electrophile. It's a positive carbon. Again, this bond is polarized. And we'll refer to the bromine up here as our leaving group. So every time you do a substitution reaction, you have a nucleophile, an electrophile, and you need a leaving group. And we're going to talk about these and how you can control this reaction by, well, your substrate here, the nucleophile, the nature of the nucleophile, and of course the nature of our leaving group. The reaction is very simple. Nucleophile attacks the electrophile, and the leaving group leaves. All right. Once again, I guess it says, this is an Sn2 reaction. And the reason that it is an Sn2 reaction is that kinetically, in our transition state, we're going to have this electrophile. We also have to have the nucleophile present. So they're both present reacting at the same time in our transition state. Now, as you probably learned, hopefully learned in general chemistry, whenever you have two molecules in the same transition state, the rate of the reaction depends on the concentration of both. That's second order, and that's why this is Sn2. 2 stands for second order, two things in the transition state. Any questions? Well, we've drawn this mechanism 2 or 3 times. I don't particularly want to stress this too much, but you do need to know where these things come from and get an appreciation as opposed to simply remembering. There are 2 basic mechanisms that you can write for a displacement reaction or a substitution. One would involve front-side attack. In a front-side attack, our nucleophile would attack the electrophilic carbon. The leaving group would leave. This is what our transition state would look like, and we wind up with this product. Again, in the transition state, we have both our original electrophile, that's this guy. Here's our nucleophile. Our bond is being made and broken at the same time. So that's one possible mechanism. The second mechanism is a backside displacement. In the backside displacement, the nucleophile is going to attack the electrophile. When it does, we have this transition state with this guy entering, this one leaving at the same time, same kinetics, they're both here, and we wind up with a product. Now, there are lots of ways that we can model what's happening here. We'll find out in just a bit that this is actually the proper mechanism. But let's just look at this and see why and how we say that. One of the things we can do these days is to model transition states using computers. What we do here, this is bromine attacking bromine leaving. And here's our carbon that was formerly bromomethane. Our transition state would be like this, with this one coming in, this one leaving, both at the same time. One of the things we can do is to calculate the charges on the various species as this transition state happens. And for a front-side attack, what we get here is a minus 0.23 on our entering group, same thing on our leaving group, and a negative charge here on our carbon. You can kind of see that. Here's the carbon here. It's a big red spot. The problem with this is that bromine is more electronegative than carbon, isn't it? So this just doesn't work for the carbon, which is now minus 0.7, and this is minus 0.23. If we do the same modeling here for our backside attack, here's our bromine coming in, here's the bromine leaving. We actually wind up with a positive charge now on our central carbon. That's this guy. And a nice about minus 0.7 on our entering group and leaving group. Once again, because bromine is more electronegative, this is a more stable transition state. So our prediction, based on modeling, would be that this guy works. The actual resolution to the problem was done many, many years ago. And that's because the backside mechanism proceeds with inversion of stereochemical conformation. So let's say we have this compound. This is a pure isomer. If we put our rankings around here, bromine will be 1, ethyl group would be 2, methyl 3, going this way. This is R, 2-bromobutane. Okay? When you do this substitution reaction, you get 2-chlorobutane. Let's do our ordering here. This is going this way. This is S, 2-chlorobutane. So what we have done here is to invert the stereochemistry at this carbon. Remember, the highest priority group here, in both cases, is the halogen. And that means that this has been inverted as the reaction proceeded. If we had a front side attack, something like this, in the front side attack, this carbon never flattens out. It stays pyramidal. So this comes in, this leaves, we would get retention of configuration. So based on this, many, many years ago, using polarimetry, which is what we're going to use tomorrow, they were able to determine that these things really do undergo backside attack to give inversion of configuration. Now, we've seen this movie many, many times. It's kind of a neat movie. Once again, as we're doing a backside attack here, you'll note that the carbon in the middle goes perfectly flat. That's our transition state. And this thing flips back and forth like an umbrella in a big windstorm. Any questions? I can just sit and watch this all day. Remember, our transition state here can be drawn as something like this. Carbon in the middle is planar. This and this are partial bonds starting here, one transition state, and down to here. Any questions? Another way that we can predict that this should follow a backside attack is using what we talked about earlier, and that is frontier molecular orbital theory. Now, we're not going to do much of that this semester. We won't do any of it this semester. Next semester, we'll probably touch on it. Remember way back when we were talking about molecular orbitals, we said that for something like methane, you can calculate regions of space where the electrons are. Now we have 4 atoms here in this molecule. Therefore, we have 4 molecular orbitals. This is the highest energy. These are lowest energy. We also have regions of space where electrons aren't. These are the lowest unoccupied molecular orbitals. This is the lowest energy, and this is the highest. What frontier molecular orbital theory tells us is that when you do a reaction, let's say that we are talking about our nucleophile pair, that's the one that has electrons. Electrons will flow from its highest occupied molecular orbital into the lowest unoccupied molecular orbital of the electrophile. So this will attack this to give you your product. Now, a nice demonstration of this is this very simple Sn2 reaction. This is cyanide. Nice negative carbon. It's a good nucleophile. If we calculate the molecular orbital for this, the highest occupied molecular orbital looks like this guy. The bigger these things are, the more likely the electrons are in that region. So we would look at cyanide and say, this is where the electrons are, could have guessed that, and this is where the bond making is going to happen. If we do the same thing here with something like bromomethane, this is the lowest unoccupied molecular orbital of bromomethane. Again, the size here, remember we're substituting at carbon, the size has to do with the likelihood that the electrons will be accepted at that position. So we have two choices, this big guy and this little one. This would be a front side attack, this is a back side attack. So our prediction here is that for this Sn2 reaction, electrons would simply flow from our big lobe here where they are to the big lobe here where they're not. Now again, we're not going to do this this semester, aside from this very simple introduction, but this is another way to justify exactly why backside attack happens and not front side. Yeah?
So it's always going to be backside for Sn2?
Absolutely. Always backside attack. All right. So for an Sn2 reaction, let's just think about the things that we need to remember. The rate of our reaction is proportional to both reactants. That means it's a bimolecular reaction. And all that means is that in our transition state, we have both the electrophile and the nucleophile. So they're both there. Secondly, because it's backside attack, it'll proceed with inversion of stereochemistry if you have a chiral molecule. And finally, bond making and bond breaking happen at the same time. So this reaction is simply concerted. Concerted means it all happens in one swoop. So those are the 3 points to remember here. Any questions? Substitution, nucleophilic, bimolecular. All right, let's just do a very simple example here. Take this generic alkyl bromide, react it with these nucleophiles, and very quickly just draw the products. These are all simple Sn2 reactions. Really all we have to do here, once we realize it's an Sn2, we identify the electrophilic center. That's this carbon. Our leaving group is simply going to be the bromine. What you do is take your nucleophile, add it to the electrophile, and the leaving group goes. So our first reaction would just give us a simple alcohol. Our second reaction here, instead of OH, we're using an alkoxide. So this is something like ethoxide. So CH3, CH2O minus. Same reaction though, simple as it can be. Nucleophile, attack the electrophile, leaving group leaves, and there you are. X is what we use to generally represent halogens. So let's say we had iodide here. Iodide can attack, bromine can leave, and we get, in this case, the alkyl iodide. Finally, this is a carboxylic acid anion. Remember, we have a doubly bonded oxygen here and an O minus. The O minus is simply our nucleophile, bromine leaves, and we get the carboxylate ester. So using this very simple displacement reaction, we've just made alcohols, ethers, alkyl halides, and carboxylate esters. Very, very simple, very, very powerful. Now back in chapter 9, we also looked at another reaction. There was an Sn2. And what we did here was we simply took a terminal alkyne. Terminal alkyne means the triple bond is at the end. And we have a hydrogen here that's moderately acidic. When I say moderately acidic, maybe the pKa is 19 or 20. So it's not real acidic, but it still can be pulled off by a very strong base like sodium amide. And what we did was we made this anion. And back in chapter 9, we saw that we could take a simple alkyl halide, react it with this, there's a nucleophile, there's the electrophile, and we would elaborate our alkyne, adding new stuff out here. Any questions? Let's do this with another nucleophile, and these are nitrogen compounds. The reaction itself is going to be the same thing. The nucleophile is going to attack, leaving group will leave. What you need to do in this is to realize that depending upon what nitrogen nucleophile you use, we can have a charge on our product. So very quickly, go ahead and look at these and predict the products. N3 is azide anion. We actually did the Lewis structure for azide. We do resonance forms way back in chapter 3. This simply features 3 nitrogens in a row, and the one on the end is negative. The nitrogen simply attacks, bromide leaves, and we wind up with the alkyl azide. Alkyl azides are an interesting class of compounds because they really want to lose nitrogen gas into from our azide, and that makes these extremely explosive. If ammonia attacks, ammonia is neutral, isn't it? It has 3 things on our nitrogen and 1 unshared pair. If we attack this carbon and the bromine leaves, we wind up with 4 things bonded to our nitrogen. That makes it an ammonium ion. Now this product can very easily lose a hydrogen like ammonium can go back to ammonia and wind up with a neutral amine. But the initially formed product here must be positive. Same thing here with dimethylamine. Two methyl groups, hydrogen, lone pair. This attacks. We wind up with the ammonium compound here. Once again, this can lose a hydrogen and make a neutral compound. This is trimethylamine. Trimethylamine is the lovely smell of fish, very fishy smell. The nitrogen attacks the electrophile, bromine leaves. This cannot, of course, lose a proton, so it stays as an ammonium compound. Fabric softener, things like that, are made by this type of reaction, where you have a long chain out here for R, and you keep your ammonium group as your head. Any questions? Well, this is nice and simple, isn't it? Exam 3 is coming up. I'm sure you all are feeling very comfortable. All we have to do is take the nucleophile, leaving group leaves, add it. However, it's not quite that simple. If we used, instead of a primary alkyl halide, we wind up with a different, totally different substitution reaction. Remember, we said the rate of an Sn2 reaction was dependent upon both compounds. If you have a tertiary alkyl halide, it's only dependent upon alkyl halide. Nucleophile doesn't enter in at all. Secondly, for an Sn2, we said we had inversion of stereochemistry. Here we have racemization. So we wind up with an equal mixture of stereoisomers. And finally, rearrangements happen. Now remember, we saw rearrangements when we did additions of, say, HBr and alkenes, that we could rearrange our carbocation. Same thing happens here. We get rearrangements. This is clearly not your standard Sn2 mechanism. What this suggests is that we are forming something different. If we started off here with R isomer 3-bromo-3-methylhexane and reacted it with methoxide, in a simple Sn2 reaction, we would expect to just get the S isomer like this. Once again, with this compound, however, we don't just get this compound, we also get an equal quantity of the R isomer. All right, so what's happening here? Why is a tertiary halide so much different than a primary? What it has to do with is that the tertiary compound can form a stable carbocation. So, if we took this and simply ripped bromide ion off of it, just had it leave, we would wind up with this carbocation. Now we remember, carbocations are planar. Because they're planar, we could attack from either the top or from the bottom to give our two stereoisomers. So the reaction would look like this. If methoxide attacked from the top, we would get this. This is our S isomer. That's inversion. If it attacked from the bottom, going up this way, we would get the R isomer. So what these data tell us, what the stereochemical data tell us, what the kinetics tell us, is that this reaction most likely involves a carbocation intermediate. Why is this only dependent upon the concentration of the electron? Well, simply because ripping the bromine off here, as opposed to pushing it off, is hard. Just breaking this bond spontaneously is something that doesn't happen quickly. Therefore, this is going to be the slow step without reaction. The attack of methoxide is going to be the fast step. So it's a two-step reaction. A slow step that involves only the electrophile, and a fast step that involves the carbocation and the nucleophile. This makes it unimolecular. Now, this is still a substitution. It's still nucleophilic. So we're going to call this Sn1. Substitution, nucleophilic, unimolecular. Carbocation intermediate. We saw the transition state for the Sn2. With the Sn1, it looks like this. This is our slow step, right here, to get the carbocation. This is the transition state where our bond is breaking. Once we do that, we form the full carbocation, that's here. And then the fast step, our nucleophile attacks to give our product. Slow step, only one product. There it goes. Our slow step, we're simply going to spontaneously break this bond. When we do, we wind up with our planar carbocation. That can be attacked from the top or from the bottom to give our mixture of two products. Any questions? Initially, because water is adding, we have three things on the water. Pull it off, and we're left with the alcohol. Any questions? All right. Well, we've done primary, where we get Sn2, and we've done tertiary, where we typically get Sn1. What it all really comes down to is what we've seen before, and that is carbocation stability. In general, the rule is the more stable the carbocation, the more likely you are to get Sn1. Remember, the carbocations are planar, this orbital is empty, and again, attack could come from here or from here. Formally, we'll call the carbocation carbon sp squared, again with our p orbital being empty. Tertiary, very likely to form a carbocation because it's stable. Down here, primary and methyl, very unstable carbocations. These are most likely to go Sn2, these Sn1, and these guys, well, it's anybody's guess. We'll see there are ways we can control whether we get Sn1 or Sn2 with secondary. We also know, why does this happen? When we do electrophilic aromatic substitution next semester, we will realize that an alkyl group is actually very electron releasing. If we have a tertiary carbocation here, so we have 3 methyls around it, and we model it, this is our carbocation carbon. You'll note that it's just barely pale sky blue. That's because these methyl groups are releasing electrons in towards the positive carbon. Secondary, we only have 2 methyl groups, so we can release less. And finally, with a primary, we only have 1 methyl group, big blue spot, unstable. The more you spread it out, the more stable it's going to be. Obviously, resonance stabilization does a lot here. Just for review, very quickly take the benzyl carbocation and draw our 3 additional resonance forms. Remember, when we do this, we want to take electrons from the ring and move them out here towards our carbocation. So, in terms of resonance forms, we would start by grabbing one of these, moving it in to make a double bond, and that leaves only 3 bonds here. So we wind up with our carbocation at this position. Second step, we can move this electron pair in, but that leaves 3 bonds here. And now our carbocation is out at this end. Same thing, move these down, and the carbocation shows up here. If we simply move these back, we'd be back where we started. Any questions? All right, a standard exam question for something like an Sn1 reaction would be something like this. I give you a substrate. That's an electrophile. I give you a nucleophile. And I ask you to, in box number 1 here, draw the intermediate carbocation, and in box number 2, draw the final product of the reaction. For the Sn1 reaction, our intermediate carbocation, we simply break the bond to our leaving group. Carbocation will have 2 methyls and an ethyl, and it would look like that. Drawing it nice and planar is a nice touch. Our final, you should also realize, these are nice multiple choice questions. Slow step here is the ionization step. Second one, methoxide is our nucleophile. It's going to attack from either side, and we would wind up with the ether. Nucleophilic attack is our fast step. Ionization is our slow step. Any questions? Now we don't have to worry about racemization here because we have 2 methyl groups and it's a chiral. That one good? All right, well, this one obviously won't be on your exam. But this one might. Once again, it's an Sn1 reaction. Draw your intermediate carbocation and the final product. Well, in terms of final product, we've all got this down now. We know that we're going to break our carbon-bromine bond. Methoxide is going to attack. We would all like our final product to look like that. Right? That makes everything and everybody happy. Of course, though, that's wrong. Why? Actually, the product you get isn't this one, but it's this guy. This is an example of a rearrangement. The initially formed carbocation is going to be right here. Our bromine's going to leave. We're going to make this secondary carbocation. However, carbocations can think. You can imagine it sitting there saying, oh, here I am. I'm on a secondary carbon. And my gosh, next to me is a tertiary carbon. That would be a more stable carbocation, wouldn't it? So, what happens is this hydrogen with its electrons is simply going to slide from here to here. This is referred to as a 1-2 hydride shift. 1-2 simply means it goes between adjacent carbons. Hydride, hydrogen with its electrons, simply slides over. Why? Because we're going from a secondary carbocation to a tertiary.
It's only for Sn1, right?
Yep. Once we have the tertiary, methoxide adds, and there's our product. Now, people sometimes have trouble with hydride transfers. It's really not magic at all. This is a little movie. Here I put a positive charge on this terminal carbon, so it's a primary carbon. And here I have a secondary carbon next to it. All the hydride transfer does is this hydrogen with its electrons just simply slides from here to here. Oops. What happened? That's not my fault, I don't think. Okay. Let's try this again. There it goes. I'll step away from it. But as you see, this hydrogen with its electrons just slides from our secondary center here over to the primary, and we wind up with our new carbocation. Not magic at all. Go ahead, draw the intermediate carbocation, draw the final product. On the exam, just like here, I would clearly tell you that we're doing an Sn1 reaction. Bromine's going to leave. And we're going to get the intermediate secondary carbocation. Now, imagine you're this carbocation being very anthropomorphic. You look at this and you say, I'm a secondary carbocation, but oh my goodness, that's a benzyl carbon. Therefore, this hydrogen is going to simply slide over, and we'll make our benzyl carbocation. Initially formed carbocation, most stable carbocation after rearrangement. That's the way it reads on the exam. Then we add our nucleophile to get our final product. Any questions? One more here. Once again, Sn1 reaction. Initially, our bromine is going to leave, and we're going to make a secondary carbocation. However, this guy is sitting here next to a quaternary carbon, something with 4 things on it. Now, just like we can slide a hydrogen, we can also just grab one of these methyls, let it slide to our positive center here, and form the tertiary carbocation. Tertiary carbocation then adds the nucleophile to give our final product. The only rearrangements that we would do on an exam would be a simple 1-2 hydride shift, or like in this case, a 1-2 methyl shift. That's the only 2 you need to think about. All right, products for Sn1 and Sn2. If you are told you have an Sn2 reaction, all we do is let the leaving group leave, add the nucleophile to that spot, and if it's a chiral center, make sure you invert the configuration. So that's what you need to know for Sn2. For Sn1, we're going to, number 1, remove the leaving group. Number 2, Going to look at our carbocation and ask, do we need to rearrange this? Once we have the most stable carbocation, we simply add the nucleophile. You don't have to worry about stereochemistry because you get a mixture. Any questions? Well, let's go ahead and just do, again, a simple set of Sn2 reactions, as you might see on your exam. On the exam, I would tell you that these are all Sn2 reactions. In our first one, we have benzyl bromide, very reactive compound. Methoxide is our nucleophile. Bromine is the leaving group. We simply make the ether. Our second one, this is phenoxide. Chapter 17, we will do phenols, simply an OH here and a phenol. This is simply an alkoxide, just like this one, going to attack the primary carbon. Bromine leaves, and we make the ether. This is an alkyne. This end is an alkyl bromide. Remember, we can't do anything with the alkyne unless we make it into an anion first. So it's just going to sit there. The oxygen here is going to attack, bromine will leave, and we will make the ester. Now, we would be pretty poor at chemists if we just simply let the fact that they're Sn1 and Sn2 go without trying to control it. Turns out that we can control whether Sn1 or Sn2 happens by controlling either the nature of your substrate, the nucleophile, or the solvent. The substrate. We've already seen this. We know that tertiary is going to be bad, and that primary is going to be good. We'll see that the nucleophile is going to matter. If we have a strong nucleophile or a weak one, we can control it based on our leaving group, and perhaps most importantly, with the solvent. Let's just look at these. The least reactive in an Sn2 reaction would be a tertiary center. The most reactive would be down here, a simple methyl group. Now the reason for this isn't anything really fancy. If we just look at a tertiary center and a methyl group, remember that when this reaction occurs, the nucleophile has to be able to get to this carbon, doesn't it? If you have a tertiary alkyl halide, we have all of these methyl groups in the way, and basically they just block it. With a primary, there's virtually nothing in the way, just a bunch of hydrogens. There's no steric crowding, and that's why methyl is so much better than tertiary. You can appreciate this more if you look at models. This purple thing is the carbon we're trying to hit. You can barely see it here. Big, big target right here. Very, very simple and intuitive. Now, if simple and intuitive doesn't work for you, look at modeling of our transition states for an Sn2. This is the Sn2 transition state, bromine in, bromine out. This is methyl group in the middle, same thing. What we can do here, just like we did earlier, is to look at the distances and the charges. Because we have all these methyls in the way, this distance right here turns out to be about 2.9 angstroms. Without the hydrogens in the way or the methyls, we can get down to about 2.5. So we can get much, much closer. Likewise, because these are further apart, we're going to get charge distribution. Very, very positive here, much less positive here, because the anions are closer. The actual numbers are something like this, minus 0.88, minus 0.69. That's a big difference. So steric bulk is probably the biggest thing determining Sn1 to Sn2. Our nucleophile. If we have a very strong nucleophile, like methoxide, that's going to be very good at getting in there and kicking the leaving group off. It has lots of electrons, very basic thing. This is good. If we're down here with something that's a very weak nucleophile, so a weak base, these electrons are spread out all over the carboxylate or the ring. These are relatively poor nucleophiles. So the stronger the base, the better the thing is at an Sn2. If you're dealing with something that isn't oxygen, you can look at your periodic table. In general, as you go down a group, these become much, much better nucleophiles at Sn2. So iodide is much, much better than chloride. So that's how you can push it Sn1 or Sn2, depending on your nucleophile. If you're dealing with an acid, you want a strong base, oxyacid, strong base. If you're dealing with a halogen, you want to go down your periodic table. That gives you more Sn2. The nature of the leaving group. This is a little more complicated. If we have something like an alkoxide, very strong base, it's a lousy leaving group. Tosylate. Tosylate, we'll see next semester. This is a very weak base, strong acid. Actually, it looks like this, toluene sulfonic acid, pKa of about -5. So very, very strong acid. That makes it a very good leaving group. Very good leaving group, strong acid, weak base, strong base, bad. And finally, the thing that is probably best at controlling, more reactive, very reactive at Sn2. But the thing that is perhaps most important is your solvent. Think about it. If you're going to do an Sn1, you're going to make ions, aren't you? If you want to dissolve sodium chloride, what do you use? A really polar solvent. Well, if you use a really polar solvent, you're much more likely to get ions. If you use a nonpolar solvent down here, you are unlikely to get ions. Magic solvent here. These are called magic solvents, actually are. DMSO is everybody's favorite. Looks like this, dimethyl sulfoxide. It is polar, doesn't have a proton. Something in DMSO should scream at you, I am Sn2. All right, if we want Sn2, we want an unhindered substrate, so primary or methyl. We want a good, strong nucleophile. We want a low pKa leaving group, something from a strong acid like toluene sulfonic acid, and nonpolar or DMSO. Nice little bullet points. You can remember all of these will give you Sn2 preferred. This mostly has to do with secondary carbons, because primary carbons are almost always Sn2, tertiary are almost always Sn1. Any questions? All right, well, you know, I guess I also listed the Sn1 preference, one tertiary, weak nucleophile, and most importantly, a polar solvent. All right. Just when you thought it was safe to design a reaction, turns out that it's not. Because in addition to simple substitution effects, if you have a secondary or a tertiary alkyl halide, you also get elimination. This is a reaction of the same thing. You get both this and the alkene that are present. What's happening here? Here's our tertiary alkyl halide. Remember we said that ionization was the slow step? Because it doesn't just want to leave. Gotta kind of kick it, push it, whatever. Well, you've got this long base floating around in there. Strong bases can not only serve as nucleophiles, but they can also serve as a simple base. Here, methoxide can pull off a proton. The electrons from this bond move in, leaving group goes, and presto, we have an alkene. Now, you know, that's not a bad thing, because we know scads of reactions of alkenes, don't we? Know lots of things we can do with alkenes. So, synthetically, this is a good thing. We can make an alkyl halide, do elimination, make an alkene, and then do whatever we want with it. But trying to figure out how to control this is going to be the tough part. Because we're doing an elimination here, and because our base is pulling off this hydrogen at the same time that our leaving group is leaving, this is bimolecular. They're both in the transition state. It's not substitution anymore, it's elimination. Therefore, we call this E2. Elimination bimolecular. All right. We're going to look at two possible ways that this elimination reaction can occur. Of course, only one will be right. What we're going to do is pull hydrogen off on the opposite side of our leaving group or on the same side. We're going to be able to distinguish the proper mechanism by just looking at the nature of our product. So here we have this guy. Got a couple chiral centers in it. What I'd like to do is to take this, do an elimination reaction using terp-butoxide as my base. Now, I'm giving this away, but terp-butoxide is the key thing to look for when you want elimination. When we do this with this substrate, this pure substrate, the only product we get is the cis isomer. Based on that, we're going to figure out exactly how this is happening. So step one, I'm going to take this and I'm going to redraw it as a sawhorse. Now, note that in this drawing, the bromine is going back, the phenyl group is going back, and these guys are all coming forward. Everyone see that? So if I take and I draw this now as a sawhorse, the phenyl and the bromine are on the same side, phenyl and bromine are on the same side, methyls are on the same side, so are the hydrogens. Okay, we're all happy with that. Now, I'm going to rotate this 60 degrees just to get this phenyl group down in this position. So the rotation I'm doing is basically this. Move the phenyl group down to here. And so this is what we've got. All right, to do our elimination, we have to pull a hydrogen off, and the leaving group has to leave. The way I've drawn this is nice and simple. Terp-butoxide pulls this off, the electrons go in, bromine leaves. We call this a trans elimination because this and this, hydrogen and the leaving group, are on opposite sides of the molecule. This is also referred to as anti or anterofacial. The other thing that's important to note here is that the hydrogen and the bromine are in the same plane. So they're anterofacial and they are coplanar. Why is that important? Well, because remember, you're building an sp squared center here and here. These have these p orbitals that have to align. So these two p orbitals have to align. They're formed when this one breaks, the electrons go in. That's why they must be coplanar. When we do this, pull this off, note the methyls are on the same side, and this is our cis isomer. Now this is the proper mechanism. But just to be honest about it, let's take our starting thing here, and instead of going this way, I'm going to rotate the phenyl down here, which puts the hydrogen up. So here we are. Here's our bromine. Now these are both coplanar, aren't they? So that's good. But if we let the terp-butoxide pull off the hydrogen and the bromine leave, we would wind up with the trans isomer. This would be called a Sn or superfacial or cis elimination. They're very, very rare. very high energy. Trans elimination is what you typically see. Now, just to make it official, let's look at the movie. Very simple movie here. All we're doing is an E2 elimination. Oh my gosh. For some reason, it just isn't liking this, is it? Okay. All right, here we go. We're going to bring in a strong base. We're going to pull off our hydrogen. Here's our leaving group. Our transition state, pulling us off. This is leaving at the same time. And you see how we grow our pi system as this reaction goes. Once again, this is a concerted process. So E2 looks a whole lot like Sn2. These guys must be trans. Reaction coordinate looks just like this. One hump, this goes at the same time. Any questions? All right, what's an exam question look like? Here we have a simple cyclic alkyl bromide. I give you a base, and I tell you I want the product for an E2 elimination. Go ahead and draw me a product. Well, okay, we can do this. We look and we see our base has to pull off a hydrogen. Our leaving group has to leave. We have a hydrogen here. We have a leaving group. They must be coplanar. Our base simply pulls this off. So here's our two guys. Our base pulls it off. Bromine leaves. And we get this as our alkene. Everyone happy with that? Well, there's a good chance you could have put a different product down, though. Because if you look at this, we not only have a hydrogen here, we also have hydrogens here, don't we? So, instead of that, we could just take the hydrogen from this carbon, pull it off, move it in, bromine leaves, and we would make this isomer. Now, it turns out that you don't get these in equal quantity. This is what you mostly get. This is a very minor product. The reason is simply something called Zaitsev's rule. Zaitsev is spelled with a Z. And it says, when you're going to form an alkene in an elimination reaction, you want to get the most highly substituted alkene. Now remember what we saw about methyl groups releasing electrons? That's why. We know that alkenes are electron deficient, and the more alkyl groups you have attached, the more stable it will be. So Zysev's rule simply says we get the most highly substituted alkene in the reaction. Any questions here? Well, you know, we've done Sn1, Sn2. We just did E2. Just to be fair, there also has to be an E1. E1, you're going to do the same thing you do in an Sn1, except the carbocation is going to lose a proton to give the alkene. The reaction would look like this. This is going to pull off a hydrogen. Polar solvents are going to promote it because we want E1 or unimolecular kinetics. And the slow step is going to be pulling off the bromine. Mechanism would look like this. We start off with a thing. Put it in a polar solvent. We form our carbocation. Now instead of the nucleophile adding here, pull off this hydrogen to make the alkene. Just like Sn1 reactions, these are ugly. We can get rearrangements. Basically, you want to avoid E1 and Sn1 because they're just so messy. But they do exist, and we must know that. The reaction coordinate looks exactly like the Sn1. Make the carbocation. We simply pull off the hydrogen to make the alkene instead of doing substitution. We'll make an attempt to look at one more movie. Maybe not. All right, I'll try. Let me do it. Here's our tertiary alkyl chloride. Step 1, we form the carbocation. That's our slow step. Once we get the carbocation, we're just going to grab one of these hydrogens, rip it off, and we make our double bond. All right. Sn1 versus, Sn2 versus E2. Those are the two we really want to worry about. If we have a simple unhindered nucleophile, we're going to get substitution. This guy is the magic thing for Sn1. E2. Sn2, E2. The reason simply has to do with the size. If we took this guy and did a simple elimination, instead of elimination, we would get 100% substitution. If we took this compound with terbutoxide, we would get 100% elimination. Whenever you see terbutoxide, it screams at you, elimination, final electron, E2 reaction. Look at the models. This is wide open. This is really hindered. And that's the real reason that this happens. The other thing you can do in terms of our base strength, if we have a weak base, you're probably more likely to get Sn2. But again, the one thing I want you to remember is terp-butoxide E2 reaction. So let's summarize it all. For Sn2, we want a simple, unhinged substrate. Got a good nucleophile, good leaving group, mostly nonpolar or aprotic. Just like terp-butoxide, the key word here is DMSO. For E2, terp-butoxide, that's all you have to remember. And Sn1 and E1, pretty much you want to avoid these. Polar solvents, good leaving groups, stable carbocations. All right, exam question. These are all simple elimination reactions. How do you know that? Terp-butoxide. Very quickly, draw the alkenes. It's an E2 reaction. Don't have to worry about rearrangements. We're simply going to pull a hydrogen off the benzyl carbon here. Bromine's going to leave. And we get styrene. Tosylate. Great leaving group. Great leaving group. But we have terp-butoxide present. We're simply going to pull a hydrogen off one of these guys. This leaves, and we get the alkene. Now we all know and love Saint-Saps rule. We look at this and say, okay, I'm going to get my most highly substituted alkene, right? That would be across here. However, that's what you get. Or Saint-Saps, huh? So much for his rule. Why is this? Remember, when we do an E2 elimination, the hydrogen and the leaving group have to be coplanar, right? So in terms of a six-membered ring, we would have to take this, do a ring flip. But when we do that, this hydrogen is equatorial and this is axial. So you can't do the elimination here. The only axial hydrogen is this guy. Therefore, this and this react. Terp-butoxide pulls this off. Bromine leaves, and that is our alkene. A little bit of a trick question, but remember, they must be coplanar. And finally, let's end this chapter with our very first two-step synthesis. Two reactions. I give you cyclohexene, and I want you to make cyclohexadiene. Now, next semester we will do 2 and even 3-step syntheses all the time. So this is our first. What you do when you're doing a synthesis is you want to start at the end. You look at it and you say to yourself, what is it? How do I know to make it? You can peek at your starting material so you know what you're working with. But What is this? Well, it's an alkene. How many ways do we know to make alkenes? Just one. Just one. Elimination. All right, so if we had a leaving group here, we could do an elimination to give us our double bond. Does that make sense? All right, let's pick a leaving group. I'm going to pick bromine because it's a nice, happy, simple leaving group. Our leaving group had to be attached at this carbon. Our elimination conditions are simply going to be tert-butoxide and tert-butanol. Why do we write those? Because we want E2, correct? And what's our intermediate compound? Well, it simply had to have a leaving group at this carbon. Therefore, this would work. Tert-butoxide pulls off a hydrogen here, and we make our conjugated diene. We're halfway there. Somehow we have to take our cyclohexene and make this. So now we look at this and say the same thing. What kind of compound is it? And how many ways do I know to make it? Well, it's an alkyl bromide, correct? But the bromine is attached adjacent to the double bond. Remember what that is? That's called an allylic bromide. And we learned a very, very simple way to make allylic bromides in chapter 10. That was, we could do free radical bromination. And because the radical adjacent, that is at the allylic positions, is so stable, we only get bromination at this one point. So how do we do allylic bromination? We simply need bromine radicals. The standard recipe to make them: in bromosuccinimide, shine a light on it, usually sitting in something like carbon-10. You can also do it with bromine in carbon-10 on a sunny day. All you need is a bromine radical. Two-step synthesis. You start off with cyclohexene, 2 allylic bromination to give the allyl bromide. Dump in tert-butoxide, do the elimination, and you get your product. On your third exam, you will have a simple two-step synthesis. Okay, so think about the logic. We have exam review on Wednesday. We'll go over some examples so you can figure out what to look for. Once again, polarimetry tomorrow. Please go to Blackboard, get the handout. There's also a video on how to use the machine. We'll look at the video again before lab, but take a look at it. It's actually a simple and fairly fun lab. If you would, please hand in your take-home problem sets. And I'll see you tomorrow.
Is there like a staple I could use?
I don't know if it has staples or not. We'll try.
Works.
By gosh, it has staples.
Yeah, staples.
Well, we're lucky. Hasn't run out of staples yet.
Just got a question. This keeps bothering me right here. You gonna staple that? I got a
Yeah.
question. So like this, I heard you could, if you could just tell me the answer, like I'm not gonna switch it, obviously, you